Welcome to the lesson on arcs of a circle. At the end of this lesson, you will be able to prove that congruent arcs of a circle subtend equal angles at its center. You will also be able to prove that the angle subtended by an arc at the center of a circle is double the angle subtended by the arc at any other point on the circle, and that an arc subtends equal angles at all points on the circle in the same segment of the circle. You must have played with toy bows and arrows as a child. Here are 5 bows. Let's use these to learn more about the circles. But first, can you spot which of these are identical? Did you get it right? Yes, these two are identical. We say they are identical because when placed one over the other, they completely overlap each other. Now, let us do something much more interesting with these bows. Let's place these 5 bows together like this. What do we get? A circle. Can you see the 2 identical bows? What do they represent now? The curved parts of the 2 identical bows represent 2 congruent arcs, AB and CD, and the string of the bows represent 2 equal chords, AB and CD of the circle. We call them congruent because they superimpose each other completely. Before we move on to study a few properties of congruent arcs of a circle, let us look at the condition of the congruency of arcs once again. As you can see, here are 2 arcs from 2 different circles. They are of the same length, but they do not superimpose each other completely. This is because these arcs are curved differently. These arcs are not congruent. Now, let us return to the circle we formed. Here, if AB and CD are 2 congruent arcs of a circle, what can you say about the chords AB and CD? Simple measurement shows that AB and CD are equal in length. Thus, we can say that the chords corresponding to congruent arcs of a circle are equal. The converse is also true. If AB and CD are 2 equal chords of a circle, their corresponding arcs are congruent. Now, let us use the properties of congruent arcs of a circle to prove a theorem. The theorem states that congruent arcs of a circle subtend equal angles at the center. Now, we have to prove that if AB and CD are 2 congruent arcs, then angle AOB is equal to angle COD. To prove the theorem, let us draw corresponding chords from the arcs AB and CD. As you can see, angles subtended by arcs AB and CD at center O are equal to the angles subtended by their corresponding chords at the center. In this figure, chords AB and CD are equal since we have already seen that chords corresponding to congruent arcs of a circle are equal. We already know that equal chords of a circle subtend equal angles at its center. Thus, angle AOB is equal to angle COD, and the theorem is proved. How many types of arcs do you find in a circle? A chord divides a circle into 2 arcs. The shorter arc is called minor arc, while the longer one is called major arc. If the chord is the diameter of the circle, it divides the circle into 2 equal arcs, each of which is called a semicircle. Next, we'll discuss the theorems related to arcs. The theorem states that the angle subtended by an arc at the center is double the angle subtended by the arc at any point on the remaining circle. Let us prove the theorem simultaneously for a minor arc, major arc, and a semicircle. In the given figure, we have an arc AB. Consider any point C on the circle that is outside AB. Now, here we have to prove angle AOB is equal to 2 times angle ACB. Before we start with the proof, consider a line joining point C to the center O and extend it to a point D within the circle. Consider triangle OAC in each of these figures. In each case, angle AOD is the exterior angle of triangle OAC. Since the exterior angle of a triangle is equal to the sum of its interior opposite angles, angle AOD is equal to angle OAC plus angle OCA. Also in triangle OAC, OA is equal to OC since they are radii of the same circle. This makes triangle OAC an isosceles triangle. This also means that angle OAC is equal to angle OCA since angles opposite to equal sides of a triangle are equal. This also means that angle AOD is double the angle OCA. Similarly, in the triangle OBC, we can prove that angle BOD is double the angle OCB. From these results, we get the sum of angles AOD and BOD is double the sum of angles OCA and OCB. This clearly shows that angle AOB is double the angle ACB. Thus, the theorem is proved. Please note, in case of the major arc, the reflex angle AOB will be double the angle ACB. Now consider another point D on the circle in the same segment as point C. What can you say about angles ACB and ADB? The theorem states that angles subtended by an arc at all points within the same segment of the circle are equal. So, we have to prove that angle ACB is equal to angle ADB. By the theorem, the angle subtended by an arc at the center is double the angle subtended by the arc at any point on the remaining circle. We can say that angle AOB is double the sum of either the angles ACB or ADB. Thus, angles ACB and ADB are equal and the theorem is proved. Here is an interesting property of angles formed by an arc in a semicircle. All angles formed in a semicircle are right angles. Let us try and prove this. Draw a diameter AB to divide the circle into two semicircles. Now, consider arc AB. Take a point P outside AB on the circle and join AP and BP. By the theorem that states that the angle subtended by an arc at the center is double the angle subtended by the arc at any point on the circle, we have angle AOB is equal to 2 multiplied by angle APB. Since AOB is a straight angle, we get angle APB is equal to 90 degrees. By the theorem, we also know that all angles subtended by an arc in the same segment are equal. This means that angles AQB and ARB are also right angles. Thus, we can say that all angles formed in a semicircle are right angles.